we're assuming is 1, so you get 1. So 0 plus 1 is 1. And here's the punchline. That means that f of 0 is 1. Ooh, taboo. Contradiction. Not allowed. Right? Because we had a theorem just before that the unit, the E of this is Z3, will map to the 0, the unit of Z2. But we've got it mapping to 1. Contradiction. Can't do that. Right? So in other words, the assumption that f of 1 is 1 is false. We've got an argument by contradiction, and therefore this cannot be so. Now, f of 1, it can only map in two ways, right? There are only, like here, there are only two choices. So this here, it either maps to that or it maps to that. Now, if it maps to that, we showed that this mapping F was the trivial homomorphism, right? And if it maps to 1, we get a contradiction. So there's only one possibility, right? I mean, there were two to start with, but we killed one. We killed mapping it to 1 because we've got a contradiction. So that only leaves that 1 here, this one, it can only map to that one. And if that's true, then this one maps to that one. So for these two groups, there is only one homomorphism, and it's the trivial one. There is no other. Right? We've proved that now. All right? So for this case, for these two groups, this pair of groups, the only homomorphism is the trivial one. Okay? That can happen. All right. Another example, mentioned only briefly, no real discussion here, and just leave it as an exercise for you to think about it. Similarly in the text, your group now, your G, is the symmetric group, right? The group of permutations of little n objects, and your H is I haven't specified what the binary operations. Anyway, H has only two elements, order 2, plus 1 and minus 1. I guess I must have touched it here. So F, I'll write it in again. F is your function which maps this set, G into H, G to H, and and F is defined as take any permutation from your symmetric group, permutation group, same thing, right? And becomes 1 if your permutation X is even, right? You remember the difference between an even and an odd permutation did a whole chapter on that, whole lecture, okay? And F maps the permutation into minus 1 if the permutation X is odd, right? And you do this as an exercise, show that this mapping F is homomorphic. In other words, take two permutations, X and Y, right? So you need to show F of XY equals Fx Fy, right? So that's the exercise for it. All right. Now, the next two examples, remember there are 8 in the whole chapter, gets a bit more details. Okay. Now this time you are mapping Z4 into Z2. Now, when we tried to map Z3 into Z2, it didn't work except for this trivial. This one's a bit more, what's the word? Friendly. It works. Okay, so we're trying to map Z4 into Z2. So that's mapping two groups. So how does that translate into mapping an element into another? Well, this way. So so this function maps this element of Z4, right, into this element of Z2, where the residue class number n is the same for both. So it maps n4 into n2. Modulus 4, modulus 2. Okay, so, well, let's, I mean, it's a bit abstract, let's translate it into concrete terms. Let's say n is 0, right? So 0 mod 4 would go to map to 0 mod 2. We're going to go anywhere with that? No, that's not interesting. Alright, forget what I just said. Okay, so firstly let's show that this mapping F is homomorphic. Right? So now the binary operation, we're talking about residue classes. Sets of residue classes. It's like 4 elements have 2 elements. And the binary operation for residue classes just plus, okay? So f of mn will be f of m, f of n, but the binary operation is plus, okay? Now, so f of mn, so we're trying to show that f is a homomorphism. So this is just by the rules of residue class arithmetic, so again it's this, right? Doing this again, used quite a lot. So this, you just add, remember residue classes behave like integers. So you just add these mn's, right? So you get that. Now, from the definition here, f of something mod n just becomes the something mod 2, right? So this just becomes this, right? From here. Use this, so this becomes that, right? Now, use this again, but in reverse, right? So you can rewrite this as that, right? Before we added these two to get that, now we're going the other way, right? So that's that. But what is this? Well, it's this, right? Except we've got an m here. So this will just become f of m4. And now it's the same, n. So this will just become f of n4, right? Well, that means this is that. So f of mn is like f of n, f of n. Right? So that is that. And therefore this function is homomorphic, right? Because that equals that. Alright, let's move on. And here gets a bit more complicated, more involved. But well, imagine, and this is something I'm becoming increasingly conscious of, my history of the development, the creation of this mathematics is lacking. I need to study up on that. I've become, during the course of the lectures on this particular course, lecture set, on finite group theory with this Barnard text, I've become very conscious that I don't have enough history knowledge of developers. But imagine you're some research mathematician, and you're learning about homomorphisms, and then you're playing with it. Imagine you're the first to do this, and once I'll make a kind of analogy in talking about the process of discovery. Represent concepts, mathematical concepts, as islands. Right? So you've got to imagine a whole bunch of islands, and then imagine an airline company, and how many different airline routes could you make between one island and another? Well, if you have n islands, there's pretty well n squared ways you can fly from one island to another, because the direction's dependent. So that's like the square of the islands. So consider just one flight route, from island A to island B. call that a kind of connection. Well, by analogy, there's the square of the number of connections between the islands as the number of islands. Hugely more. If n's large, n squared is huge. Okay. So similarly in mathematics, when you have quite a few concepts, ideas like homomorphism, isomorphism, whatever, groups, the number of connections you can make between the concepts, also is of the order n squared. So the more concepts you have, analogous to islands, the more concepts you have, the more connections, hugely more connections you can make between the concepts. So, like, one concept would be the product group, right? And here you are now thinking about homomorphisms, and somebody had to ask the question for the first time, well, could you have a homomorphism between product groups? Is that possible? How would you do that? How would you define the mapping? Like, imagine you have two groups, and we're going to form the product group of these two, G1 and G2, and let's say already that there is a homomorphism between G1 and H1, and there's a second homomorphism between G2 and H2.